Hello and welcome to Bonding Lewis Structures. First, I want to talk about Lewis structures of atoms. Um, we've already learned Lewis structures of atoms, but for continuity's sake, I think it's important we revisit the topic briefly. So, Lewis structures of atoms, essentially, we draw the symbol and we draw the number of valence electrons on the atom. And so, lithium, in being group 1 with one valence electron, gets a single dot. Boron in group 13 gets 3 electrons, one at 3 of the poles. It doesn't matter which you choose, just make sure they're all singly there. We don't put pairs up until we have more than 4. Oxygen group 16 with 6 valence electrons. 2 are paired and 2 are singular. Keep in mind, you want to have them each individually at each pole and then pair after you've had 4. When we draw Lewis structures for cations, we take into account the binary ionic charge we expect from that cation. We would remove that number of electrons from the valence shell, which essentially is stripping all the electrons. Most importantly, we'll draw brackets around the atom, and then we'll put the charge outside the brackets. The brackets indicate we have a charged particle. Okay, so this is calcium being group 2, loses 2 electrons, plus 2. See, it's got no valence electrons. Aluminum group 13 is going to lose 3 electrons. Sodium group 1, 1 valence electron gets lost, and so you see the associated charges outside the brackets. For anions, we're simply going to add the same number of valence electrons that we would expect that binary anion to gain. So we have something along the lines of halogen gaining electrons. We'll draw zeros or dots for the electrons that belong to that atom, and we will draw X's for electrons that have been gained. So we'll draw the electron arrangement. So our X's will represent electrons that have been gained. We'll draw the atom with its electrons around it, place brackets around that structure, and then put the charge outside the brackets. This is the bromide ion. You can see it's got dots for its own 7 electrons, then an X for the electron it gained, brackets indicating it's an ion, then a 1 minus charge outside the brackets. Sulfide, we'd expect, is in group 16, is going to gain 2 electrons, and this is what we would see. Nitride is going to gain 3 electrons, and so the big idea here is that we have dots representing electrons owned and then X electrons gained. This right now, as we learn to draw these, is important just to indicate we know what's being lost and gained, and then the charge, of course, outside the brackets. Drawing Lewis structure for ionic compounds is simply a combination of the last two ideas, cations and anions. It's just important to note that when you draw the Lewis structure for an ionic compound that we draw for every cation our formula unit has, we draw every one of them. So if it's Ba2O for barium oxide, or not barium oxide, sorry, lithium oxide, Li2O, we would draw 2 lithium ions and 1 oxygen ion. So each ion in that formula unit gets drawn. So sodium chloride, whose formula is NaCl, we will draw 1 sodium and 1 chloride ion. Magnesium chloride is a little different. It's got 1 magnesium, 2 chloride because of the charge on magnesium requiring 2 chlorides to balance. We would expect to see 1 magnesium ion with a 2 plus charge and 2 chloride ions. So it's really evident when you draw an ionic compound's Lewis structure where electrons have gone. These 2 electrons, the X's, have been gained by the chloride, and the magnesium, of course, lost them. That's basically how it's done. So you can imagine this would get a little bit tiresome. Probably once it'll happen where you need to draw something along the lines of, say, aluminum oxide, which would be 5 bracketed ions. The structure for covalent compounds is a bit of a process, but the main idea is pretty simple. The first thing we do is choose a central atom, and just to give you a point of reference, we'd be talking like a molecule of methane. We'll choose a central atom. It'll usually be the thing written first. It will usually be the thing written fewest amount. It will usually be the least electronegative element in the molecule. It will not ever be hydrogen or fluorine. Hydrogen because it only supports 2 electrons, and fluorine because it's the most electronegative element and is not likely to serve as a central atom giving electrons. So if there's only 2 atoms in the molecule, there is no central atom. So what are we going to do? We're going to count how many valence electrons are available in the molecule. Okay, that's the main thing. And by the time we're done, we'll have accounted for every electron we counted. So once we have our central atom and how many electrons we're going to use, we're going to singly bond each peripheral atom. Then we'll fill the valence shell with 8 electrons of each peripheral atom, except for hydrogen. Hydrogen only needs 2 electrons, so a single bond will please hydrogen. You'll also, once you've done that, ensure the central atom has its 8 electrons. This is assuming there's no exceptions we'll hear about soon. If there are not enough electrons to satisfy all the octets, you'll make multiple bonds until the octets are satisfied. Elements that make multiple bonds, carbon, oxygen, nitrogen, sulfur, are the most common likely to form a multiple bond. If extra electrons remain and all the octets are satisfied, you will attach extra electrons to the central atom. We'll talk about that also in the context of expanded octets. And make sure at the end when we're done, we've accounted for all electrons and that all atoms are satisfied. Some symbology while we start this. A dash typically represents a bond between two atoms, but it can also be written as dots, like in this molecule. These are all different representations of water, okay? A pair of electrons not shared or not bonding is usually represented by 2 dots. So an unshared pair of electrons on the oxygen atom here is written like that. When the dots are between 2 atoms, it's clearly going to represent a single bond. When it's off on its own, not between an atom and another atom, then this is unshared pair, okay? Rarely you'll see an unshared pair of electrons drawn like this. This is a quick way to draw a lot of electrons when you need to. I'll do it once or twice just so you see it. It's not meant to mislead, and it's pretty evident that this means there's a pair of electrons here and here, just as there is here and here. So hopefully these representations give you a good idea that there's lots of possibilities that all mean the same thing. So let's draw carbon tetrachloride. Carbon tetrachloride is CCl4. It's got how many valence electrons? Carbon's in group 14, so it has 4 valence electrons. Chlorine has 7 valence electrons, and it's in group 17. But there are 4 atoms, so that's 28 plus 4, 32 electrons to work with. So our central atom written first, carbon, it's in fewest amount. It is the least electronegative atom in the molecule. Let's singly bond each chlorine to the carbon. And once we do that, we will go ahead and fulfill the octet for each peripheral atom using electrons we count along the way. Now remember, we have 32 to use. So far I've used 2, 4, 6, 8 on the bonds, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We used all 32 electrons. This chloride thinks it has these 8 electrons. Not chloride, pardon me, it's a chlorine atom. This carbon thinks it has 8 electrons. Now remember, in a covalent molecule, atoms are sharing. So the atom's perception is that if it's bonded, those electrons are also belonging to it. So this carbon thinks it has 8 electrons. Each bond, remember, is 2 electrons. So carbon thinks it has 8. Chlorine has 3 unshared pairs in this bond. That's 8. Each chlorine feels the same way. So the octet is satisfied for all 4 of these atoms. And this is what carbon tetrachloride would look like. You don't need to make these Venn diagram circles. That's just to illustrate atoms having electrons. Water. Water is H2O. We have 2 times 1 electron for each hydrogen. We have oxygen has 6 valence electrons for group 16, so we have 8 electrons to work with. Our central atom is oxygen. We bond singly each hydrogen. We used 4 electrons so far, but you should remember that hydrogen is satisfied with 2 electrons. And remember, this bond is 2 electrons, so hydrogen's done. There's nowhere else to put electrons peripherally. We can only put electrons on the central atom. We've used 4. We have 4 remaining. Those 4 will go on the central atom. And that is that. Each hydrogen has 2. Oxygen has 2, 4, 6, 8 electrons. This is water. We can also experience multiple bonds. Double bonds formed when 4 electrons are shared between 2 atoms. This is carbon monoxide in 2 different ways. When this representation I like a lot because at least while we're learning that it shows that carbon's 4 electrons are X's and oxygen's 6 electrons are dots. And what we see is that each atom has 8 electrons. There's 8 here, 8 here. Okay, and that's true for both sides. The dashed model does the same thing. Triple bonds are formed when you have 3 electrons or 6 electrons shared between 2 atoms. Keep in mind, a double bond is a singular thing. It's one bonding domain. Okay, so it doesn't mean there's 2 actual same kind of bonds there. We'll learn more about that soon. But a triple bond counts as one bonding domain. So it's one space, even though there may be 4 or 6 electrons there. Carbon dioxide, we just saw it, but it's important we do this work together. We have CO2, 4 electrons on carbon because it's group 14. We have 6 times 2 for the oxygen, so that's 12 plus 4, 16 electrons. So here's carbon as the central atom, singly bound to each oxygen. And so remember, we have 16 electrons. We use 2, 4, 6, 8, 10, 12, 14, 16. And at first base value, this looks good. But the problem becomes quickly, you'll see that carbon in this representation only has 4 electrons. 1, 2, 3, 4. So we have to fix that. And the trick to doing that is to, instead of putting all the electrons on the peripheral atoms, we will make a multiple bond. So we'll essentially get rid of a pair of electrons here. We're going to have to do this until it's got its octet. And we know that if we do it once, we're only going to get 2 more electrons. So now we have 2, 4, 6 electrons on carbon. Still 8 around oxygen here. So we're going to do the same thing on the other atom on the other side. So let's erase and get our purple pen back. And now we have it. We have 2, 4, 6, 8 on oxygen, 2, 4, 6, 8 on carbon, 2, 4, 6, 8 on the other oxygen. And we've used 2, 4, 6, 8, 10, 12, 14, 16 electrons. This is carbon dioxide. Nitrogen, into gas, has 5 plus 5, 10 valence electrons. Nitrogen's in group 15. No central atom because there's just 2 atoms there. And so let's use all 10 of our electrons. That doesn't work. So you should see pretty quickly that we've only got 2 4 electrons on this nitrogen. Now, if you watched closely on carbon dioxide, you should see that we need 4 more electrons to be shared with the left-hand nitrogen. So we're going to erase both of these pairs on top bottom here and turn those into shared pairs of electrons. Well, the eraser decided to stop working. Ooh, uh-oh. Spinning wheel of doom, people. Okay, the spinning wheel of doom is fixed. We took 2 electrons off here and off of here, and we will share those in between, and that's going to give us 10 electrons total. 2, 4, 6, 8, 10 used, and this nitrogen thinks it has 8, and this nitrogen thinks it has 8. This is nitrogen, triply bound nitrogen. One important little thing that can happen in a covalent bond is called coordinate covalent bonding. Rarely there are molecules that form that in order to reach an octet or stability for each atom, one atom in the bond will share 2 electrons to make one whole bond. In the case of carbon monoxide, this happens. But basically what it amounts to is instead of some bonding that is where we have equal number of electrons being shared and balanced, these 2 electrons are going to go to be the whole bond between carbon and carbon here. So we end up having, carbon and oxygen. So we end up having one of the triple bond be 2 electrons from the same atom. That is the coordinate covalent bond. The 2 blue there came from this oxygen. Typically, in a covalent bond, electrons are distributed equally by each atom. But rarely this can happen to provide stability in a molecule that otherwise would not have stability. There are some exceptions to the octet rule we need to note. Boron, aluminum, and beryllium can bind covalently due to small size and relatively high electronegativity. We already know beryllium and aluminum are metals. However, they have relatively high electronegativity values, which do facilitate covalent bonding in some bonds they form. And when that happens, we have to take account for the possibility that they are stable with less than 8 electrons. Aluminum and boron are stable with 6 valence electrons when they bind covalently. In other words, you don't need to try to put 8 electrons around it. It's stable with 6. Beryllium, however, is stable with 4. And so keep this in mind when you're drawing covalent molecules of these 3 atoms. Nonmetals in energy level 3 and higher can support more than 8 electrons when they are the central atom. And this essentially starts with phosphorus. Okay? If I'm in period 3, I have silicon. Silicon has no interest in doing this really. But phosphorus, sulfur, and any nonmetal beyond that, energy level 3, 4, and beyond, can bind and form more than 8 electrons around its central atom. Some examples are phosphorus pentachloride, sulfur hexafluoride, which, if you know, this is the deep voice gas. It is a very heavy gas. It is heavier than air, and if you breathe it, it makes you sound like you have a very, very deep voice. So Theory is that they're able to use d orbitals to support further bonding. The terminology you'll hear us say is the expanded octet. Obviously, it's not an octet anymore, but terminology in chemists, you know. Formal charge is the charge on each atom in a covalently bound molecule. There are some molecules that have no overall charge that but may have a charge on a couple of atoms inside the molecule in order to facilitate the stability. By and large, molecules are most stable when they have the smallest, fewest formal charges possible. Ideally, each atom has all of its valence electrons attached to it in the molecule. Ions will always carry a formal charge somewhere on the molecule, either a lack of or an extra electron somewhere in the ion. A polyatomic ion is the best way to say that. The octet rule applies unless the central atoms beryllium, boron, or nonmetal phosphorus are larger. Again, with our example of our coordinate covalent bond, in this molecule, we can see that the carbon has 5 electrons of its own, quote unquote, that are directly around it in the molecule, and oxygen has only 5. Oxygen has 6 valence electrons, so for it to have only 5 around it gives it a formal charge of +1. Carbon having 5 instead of 4 gives it a formal charge of -1, meaning it has 1 extra electron, and oxygen has 1 few. Example with carbon dioxide, when you first started drawing carbon dioxide with me, you saw that in our first drawing, we noticed that carbon didn't have an octet. And so in this drawing, the purple dots here would be electrons that are, quote, on the carbon. And the X's on the other end are electrons that are around oxygen. In this drawing, we see that oxygen has 7 electrons around it, and carbon has only 2. This would give a formal charge of -1 in each oxygen and +2 on the carbon. If we then transfer to make a triple bond between one of the carbon-oxygen bonds, it gives us a +1 charge on oxygen, because you should see we have 1, 2, 3, 4, 5 electrons directly around oxygen. We have a formal charge of 0 on carbon, which is fine, but on the other end we have a -1 charge on this oxygen. And so it has 7 electrons around it, where oxygen should only have 6. Carbon dioxide, the normal representation, Lewis structure, and actual shape is this shape and this structure, where we have double bonds on either side, which gives each atom a formal charge of 0. Oxygen has 2, 4, 6, carbon has 4, and that's exactly how carbon dioxide is. These two are drawings that would be incorrect for carbon dioxide because of the formal charges on atoms we find. Now, some atoms, like molecules, like we said, do form formal charges because there's no other way to draw it without a formal charge. But I think you'll find as we go through this will become easier. A great example is sulfate. Sulfate is able to break the octet rule. It's able to have more than 8 electrons around its central atom. When we first start drawing Lewis structures, and if I asked you to draw SO4 2-, you might draw this. And the reason is this is going to give us 32 electrons. 6 times 4 is 24, plus 6 more from sulfur, plus 2 gained right there in the 2-. This is what we might draw. We might think, oh, that looks perfect. It looks just like carbon tetrachloride did. However, you might notice also, though, now that we've talked about formal charge, that there's only 4 electrons around sulfur. And that's a problem. Sulfur has 6 valence electrons. It would have a formal charge of +2. That makes this structure unlikely. In addition to the +2 on sulfur, each oxygen has a negative charge. Now, when you have an ion, you're going to have some formal charge in 2 places here. You should have 2 extra electrons somewhere on the molecule giving you some formal charge, but not as much as we see here. So if we go ahead and double one of the bonds, it takes the formal charge of sulfur down to 1, and we have 3 oxygens that have a -1 charge. And if we take it up to 2 bonds doubled, we then have a structure which is consistent with stability, where we have a -2 charge that makes sense, and then we have a central atom with no formal charge. So let's draw one together. So now this is called disulfonyl fluoride, I think is the name, but we don't need to know that, so that's okay. Our central atom is going to be sulfur. We have sulfur has 6 electrons. We have 6 times 2 for oxygen. We have 7 times 2 for fluorine. That's 14 plus 12. That's 26 plus 6 more, 32 electrons. So now if you recall, carbon tetrachloride had 32 electrons. So we might start off by drawing this. Now, the first thing we should notice is that sulfur has, again, a formal charge of positive 2, because there are 1, 2, 3, 4 electrons directly around sulfur. We should expect there to be 6. Fluorine right now has 1, 2, 3, 4, 5, 6, 7. Its formal charge is 0 on each. That's how we want it. The oxygens here have a formal charge of -1. So we need to fix both the positive 2 on sulfur and the -1s on oxygen. And the way to do that is to make a couple double bonds. Sulfur is an energy level 3. It's beyond phosphorus, so it can form expanded octets. And so what we're going to do is take a pair of electrons from here and a pair of electrons from the other oxygen, and we're going to make double bonds. And when we do this, it forms a structure with 0 formal charge on every atom. This is SO2, so SO2F2, bisulfonyl fluoride. Polyatomic ions are very straightforward to draw. We talked about sulfate a moment ago. Essentially, all that's different is that we have to add or take away electrons based on the charge of the polyatomic ion. Then we need to make sure we bracket that molecule and put its charge outside the brackets. Nitrate is NO3 minus. Nitrogen has 5 valence electrons. Oxygen has 6, but there are 3 of them. And then there's 1 extra given the -1. Remember, a -1 means one has 1 extra electron. If it was +1, it would be minus an electron. So we have 18 plus 5, that's 23 plus 1, 24 valence electrons. This is nitrogen's 5, oxygen 6 times 3, and then the oxidation number, we have add 1. Now, again, if this was +1, we would take an electron away. But since it's -1, we've gained an electron. So 24 valence electrons. We have nitrogen. We have 3 oxygen bound. Okay, so now we should immediately notice nitrogen is missing an electron. They're missing a pair of electrons. Nitrogen is not something that can break the octet. It needs 2 more electrons. The quick way to fix that is to do the following. We're going to take a pair of electrons off one of the peripheral atoms. It does not matter which one. And we're going to make a double bond. And in doing that, we now have a formal charge of -1 here, -1 here, and +1 here. We're stuck at this point with nitrate. And the reason is that if we were to double another bond, we would all of a sudden have a formal charge of 5 around the central atom and be breaking the octet rule. Nitrogen can't break the octet rule. Additionally, we note that there's no way to move around these charges. So this is nitrate. Okay? Nitrate has a very interesting structure and shape. But this structure, if you'll notice, you've got +1, -1, -1, gives us the overall -1 charge. This is exactly how nitrate is. There's no way to make this more stable. Again, if you add another double bond by pulling a pair of electrons off a peripheral oxygen, it's going to give you an expanded octet on nitrogen. Nitrogen's energy level 2. It cannot form an expanded octet. Welcome to nitrate. Another interesting fact about nitrate is that that double bond we discovered just now can appear at any of the 3 different bonds in the molecule, and we call these resonance structures. Resonance structures are when you can find more than one valid Lewis structure that can be written for a molecule. And the interesting part is experimentally we find that the actual structures data shows that it's a blend of all 3 of the possibilities. So the nitrogen-oxygen bonds in this molecule are calculated out experimentally in nitrate to be 1.33 times the predicted bond length of a regular NO bond. So experimentally, we support the idea that any sample of nitrate, that double bond can be at any one of the 3 positions at any one time, therefore making a bond that's got a length of 1.33, what we'd expect it to be. Pretty cool. This was a very long video. It's got a lot of interesting details. I urge you to rewatch what you need to rewatch as much as possible. This is the end of Lewis structures. I know it hurts. I know it's tough when things end, but we do make more of these, and we will look forward to having you on the next one. Make sure you've taken high-quality notes, rewatch it as needed, and by heavens, please be asking questions in class.